String theory is a very ambitious attempt to understand the force of gravity at the quantum level, because we all understand gravity. When we throw something, it falls down. That is described by Newton's laws, and later Einstein understood gravity in terms of the geometry of space and time, that it is because the geometry is not flat that objects move like the earth moves around the sun, because that is the geometry of the earth, and the moon is creating a geometry in which this is like the simplest or the shortest path. So Einstein understood gravity in terms of space and time. But we also know that when we go to the atomic size, we need to describe things in terms of quantum mechanics. It is not very easy to understand how to talk about space and time at the quantum level. And so string theory is trying to understand how do you think of space and time at the very smallest levels when the quantum nature of space and time becomes important. And this is not only an abstract question, it is very important to understand for the origin of the universe, because in the universe, which started off with a big bang, the energies and the interactions were such that you had quantum effects. In fact, the galaxies that we see in the sky are due to very small quantum effects in the early universe, which have gotten magnified over time. So understanding quantum nature of gravity is a very important question. It is also very important to understand in the properties of black holes, which have recently also been discovered. So string theory tries to understand quantum gravity. That's one way to say what is string theory. It is a theory of quantum gravity. But actually string theory does more. It brings together the quantum mechanics, but also gravity, and also some of the other forces in nature, which we understand now, the fundamental forces like the electromagnetic force, which runs all our devices, the electricity and magnetism, the strong interactions, which are the nuclear interactions, which hold the nucleus inside an atom together, and radioactive interactions or weak interactions, which make nucleus decay by radioactivity. All these interactions potentially are brought together by string theory together with gravity. So that's one of the very attractive things about it. String theory does not try to change quantum mechanics. String theory incorporates quantum mechanics. So string theory is very compatible with quantum mechanics. It is just trying to describe how would you apply quantum mechanics when you're trying to understand space and time at the very smallest levels. Because right now we think of space and time as like a continuum. It is like in a river. You see the river is flowing with water, it looks continuous. But we know that ultimately the river is made of water molecules and atoms. So it is not continuous at the atomic molecular size. Similarly, space and time looks continuous to us. Time seems to flow continuously. Space seems to be continuous. But ultimately, at the quantum level, it may not be continuous. So string theory is trying to understand how quantum mechanics might describe space and time. Yes, duality is a very fascinating concept. I think it is there in many Eastern philosophies also, about the yin and the yang and so on. It was played a major role in the development of quantum mechanics, because we know that light has a dual aspect, one of being a wave, like a wave in string, but also like a particle, like a photon. So light has these two seemingly different aspects, but they are actually compatible. They are reconciled with each other. In some situations, you see light behaving like a particle. In some, you see it behaving like a wave. The idea of the duality is that there may be two different descriptions of the same object, but they seem very different, but they are actually the same description. So that is the duality, that there are, so one, for instance, space and time, one way to describe them in string theory, one duality which has been very important in string theory is the so-called gauge string duality. It is trying to, on the one hand, describe the space-time in terms of the geometry and how it is, like I said earlier, how it is going to be modified maybe by quantum mechanics. But on the other hand, it also says that at least for some space-times we understand that there may be a dual description in terms of a holographic description, in terms of the boundary of the space and time. It's like a hologram on your credit card is able to capture a three-dimensional reality on a two-dimensional screen, or a two-dimensional flat this thing you see, it looks three-dimensional, right? So it's somehow capturing a higher dimensional space-time in terms of a lower dimensional space-time. That's an example of the kind of duality. But ultimately it is about two different descriptions being the same. And in string theory, there were, in the beginning, people thought there were a few different kinds of string theories. And what people realized in the mid-90s was that actually there is only one string theory, and these are different limits of in different limits of the when the strings are interacting with each other strongly or weakly, you see one string theory or the other. So they are actually all the same string theory. So that's the fascinating thing about duality. Maybe one of my colleagues gives a nice example that supposing you have a room, you look at it from one window, you get one view of the room. You look at it from another window, from another side, you get a different view of the room, but it is the same room. So that's, in a way, what the philosophy of duality is. Yes, so string theory has been continuously developing, and many new insights have continuously been coming from string theory. And one of the very interesting new ones is about how ideas from quantum information and quantum computing maybe are playing a role in understanding some of the puzzles related to black holes. Black holes are objects that we have experimentally observed in the sky, coming from stars or at the centers of galaxies. But at the quantum level, and this has not yet been tested, but people believe that at the quantum level, the black holes radiate, they evaporate, and they radiate and become and eventually disappear. That leads to some puzzles, and some of the very interesting ideas recently has been about how the quantum information that is there in the black hole is somehow also reflected in the geometry around the black hole. I think that gave a whole new insight into the puzzles about black holes. So that's one very exciting area. There have been other developments in applying ideas of string theory to condensed matter systems, that is solid state physics systems, something very different. And it shows how string theory is a very powerful framework which can actually try to describe many things. So I often say that string theory is not some abstract theoretical construction. It actually arises in many natural systems. So it is not purely, I mean, it is still very theoretical, but I think it is a very natural theoretical extension of the ideas that we know. Yes, there are indeed many questions that string theory has still not been able to address. For a theory that claims to give you an understanding of gravity at the quantum level. It should explain the universe as a whole, the cosmology of the universe, how the universe began and evolved and developed and will continue to develop. And we have learned a lot about the universe in recent years by observations through some of our very precise telescopes. So we learned that the universe is accelerating in its expansion, and that the reason for that acceleration is something people call dark energy, but the string theory should give an understanding of where such a dark energy can come from, how it can be realized. It has not yet been able to do that. Of course, there are related puzzles also about dark matter, which is an unknown form of matter, which also is something we need to understand better. So string theory, I think, should give good answers to these questions about the evolution of the universe, and I think that is something it has still not yet managed to do very successfully. Yes, that is essentially something that is compatible with string theory, and in particular some of the scenarios that people have which leads to the Big Bang, a kind of an inflationary scenario of the expansion of the universe, that there was an initial phase of very high exponentially large expansion, and then in a sense it culminated in what we would call a Big Bang and the evolution of the universe after that. In principle, it can. It is powerful enough to do that. In a way, it's very interesting. Early on, people thought string theory could unify all the forces, and it is still possible that it might, though there seemed to be no unique way of doing it, and people have not yet also found a way to precisely obtain exactly all the particles and forces that we have, but it is not impossible, because there are many possible solutions to the equations of string theory, so to say. There are many possible universes that string theory allows in its equations. I think that is also a challenge for string theory, to see if it can give rise to the particular kind of universe that we see with all its particles. But it's also interesting that recently string theory has given a new way of thinking about some of the other forces that are there, like I mentioned the strong interactions, the nuclear interactions. String theory has given a geometric way of thinking about these interactions also. So in a way it has that may not count as unification, but it is giving a new way to understand how strings naturally arise in the strong interactions. Because strings are one-dimensional objects, like a rubber band or a piece of string, and you might think, oh, that's very arbitrary, why should I have a rubber band like object? But actually that's very related to very old ideas of Faraday and Maxwell about the lines of flux that we learn in our school when we learn electricity and magnetism. So what happens in the strong interaction is these lines of flux, the electric lines or magnetic lines, the similar lines in the strong interactions, they form a string. So they form a string-like object, and there is a way to describe them now through geometry, and so that is another way in which string theory has shed new light on the other forces other than gravity. In this context, you can think of it has some kind of a tube which carries electric field as an analog of the electric field or magnetic field. It's like you can imagine, actually people see similar things in superconductors, where if you put a magnetic field in a superconductor, the magnetic field can penetrate. If the strength of the field is very high, it can penetrate the superconductor and form a kind of a tube inside it, in which the magnetic field is just along the tube. There is zero magnetic field outside, but there is a small magnetic field in this tube. So it's like a pipe, if you wish, which is carrying some water. But you can think of this as a pipe which is carrying magnetic field. Yeah, maybe in high school people have learned about the solenoid, like a coil. When you have an electric coil, then there is a magnetic field inside it. It's a bit like that, you can think of it. So in some of these cases, the strings are very tangible objects. They are, they're not some fancy construction. They are very real things. Yeah, actually, I wanted to study what is called quantum field theory, which is the framework in which we normally describe all the other forces other than gravity, like the electromagnetic force, the strong interactions, the weak interactions. At the quantum level, how do you describe electricity and magnetism? There is a framework, a theoretical framework called quantum field theory, which describes electricity and magnetism in the atoms, etc., at a quantum level. So this quantum field theory framework is a very powerful one. It has helped us to understand most of the particles that we see, but except gravity. But I always wanted to know, why did people think of the idea of strings? Why is it natural? So what I said a little while ago about the strings coming as the lines of flux connects it, in my mind at least, very closely to the ideas of Faraday and Maxwell about how they were thinking about electricity and magnetism. So I feel there is something very natural about string theory, and besides, when you start working in it, you see it has a very compelling feeling. It is very elegant, it is very mathematically consistent and very tight. You cannot kind of easily destroy it, and at the same time it gives you a lot of new insights, new ideas, for instance, about subjects that people had studied earlier, like general relativity of Einstein or quantum field theory. It gives you new insights about these things in a very miraculous way. So that's, for me, something very compelling.